Geometric series. A geometric series is taking a geometric sequence and finding the sum of all the terms. So we do have a formula that we can use to find the sum of a finite geometric series, meaning that it has an end to the sequence. So here is our formula. Make sure that you write it down because you will be required to remember this. Example 4. Use the formula for the sum of the finite geometric series and write our sigma notation in expanded form. Remember, this oversized e is actually called a sigma, and it means to find the sum of terms. It is specifically asking us to find the sum from the first term to the 7th term. So we need to write down all 7 terms. Right next to the sigma is the explicit formula. So we're actually being told that a sub 1 is equal to 3 and r is 2/3. So we can use that information to come up with our sequence and therefore solve our series. So if a sub 1 is equal to 3, a sub 2 is 3 times 2/3 raised to the exponent of 2 minus 1. I'm just using the explicit formula that was given to us. When this is simplified, it simplifies to be 2. A sub 3, we use our formula again, 2/3. We are just subbing in our n value as 3 because we're trying to find the third term. This simplifies to be 4/3. A sub 4 simplifies to be 8/9. A sub 5 is 16/27. A sub 6 is 32/81, and a sub 7 is 64/243. So if we're going to actually find the sum, then I don't want you just to add these numbers together. The reason why we found all of these numbers is because the question's asking us to write this in expanded form. So here is our expanded form, and now we're going to use our finite geometric series formula to actually find the sum. Here is our formula, so we're going to sub in what we know. N is equal to 7, so we're finding S sub 7. The value of the first term is 3. 1 minus r, r is 2/3. And then raised to the 7th, because that's in the formula, over 1 minus 2/3. Practice putting this into your calculator because the parentheses are important. You should simplify this to get 2059 over 243. Example 5 gives us a geometric series. Notice that in series we have addition signs between the terms rather than commas, which you would see for a sequence. Just something I'm pointing out. Now we're told the first couple of terms and then the very last term, but we don't know which n value is represented here. So we're going to use our formulas that we've been given, our explicit formula, and solve for that. We know a sub 1 is equal to 200, and we can solve for r because we can take the second term and divide it by the first term. So we end up getting 1.5 for the value of r. a sub n is equal to a sub 1 times r to the n minus 1. I'm not using my sum formula because I'm not given a sum. I'm only given the value of the individual terms. We're going to solve for n. So we don't know what n is, but we do know that the value of that last term is 7,688.7. So we can divide both sides by 200. And we're left with 1.5 n to n minus 1 and 38.4435. Now we need to solve for a variable that is in the exponent. We first look, can we make the number on the left-hand side equivalent to 1.5? i.e., can we make the bases the same? Because really this is just an exponent of 1 on the left-hand side. We cannot, so therefore we must use our logarithms. So we're going to take the log of both sides. Remember, as long as you are consistent on both sides of the equations, you are fine. Once we insert that log, we can take our exponent and bring that to the front as our multiplier. We're trying to get the n by itself, so we will divide both sides by log of 1.5. So we're left with n minus 1 on the right-hand side and log of 38.4435 divided by log of 1.5. Then we will add 1 to both sides to isolate n. We turn to the calculator and we put that into our calculator and we get approximately 10. Now remember, you cannot have a decimal here because n represents the number of terms. In part B of example 5, we're asked again to come up with the number of terms. The difference here is instead of getting a series written out with the value of the terms, they're giving us the value of the sum. The sum is 11,718. Because they're giving us the sum, we will use our sum formula. So let's plug in what we know. The sum, the value of the first term is told, it's 3, and we're also told the common ratio. If we look at this denominator, this can be simplified to -4, and then we can multiply both sides by -4 to cancel the -4 on the right-hand side. So we're left with 3 times 1 minus 5 to the n on the right-hand side, and negative 46,872 on the left-hand side. We can divide both sides by 3 because we're trying to get to the inside of the parentheses to use that n value. When we divide by 3, negative 15,624 is equal to 1 minus 5n. I'm going to bring these highlighted parts to the other side, only because I like to work with positive numbers. So I have 5n on the left-hand side, but now it's positive, and 1 plus 15,624 on the right-hand side. I'm going to simplify the right-hand side, and then I'm going to take the log of both sides. I'll use that power property and bring the n down in front. And divide both sides by log 5. They cancel on the left, so we get n is equal to 6. Here is a slide that puts all the information in one spot. Your recursive formula, your explicit formula, and your finite geometric series formula.